last periodic trend is electron affinity, especially on the right side of the periodic table for nonmetals. It's often easier for electrons to gain an electron rather than lose one. So electron affinity is the energy change associated with attaching an electron to an atom. So we have a neutral atom A, attach an electron to it to make the minus ion of it. And we'll see that for different cases, this can be both positive or negative. Sometimes atoms will require us to put energy in to make this change happen. Sometimes this will be an exothermic change. So here's the list of electron affinities for the different atoms. We can see both positive and negative numbers in different cases here. Remember that in this case, that a negative answer here, it's like a reaction enthalpy or reaction energy. Negative means that energy is released when this process occurs. So the higher the Z effective, the higher the effective nuclear charge, we'd expect to see more energy released when we add an electron to that atom. And that is, in fact, what we see. So for fluorine here, 328 kilojoules of energy is released when you attach an electron to it. So that's quite exothermic. It's very favorable to attach an electron to a fluorine atom. On the other hand, lithium, it's only slightly favorable to attach an electron to, -60. Beryllium, you can attach an electron to the atom, but you have to actually put a lot of energy in to make that happen. So it's an endothermic process. So there are these signs associated with electron affinities, and that is a slight, thing you have to worry about when looking at electron affinities. But Z effective is really the main trend here. We can see there's not really a trend with the shell N. Very much there is on this side, I guess, that it's better to add an electron to a 1s electron here compared to a 2, 3, 4, 5, 6s electron. But over here, there's not much difference. It stays about the same, largely just because the electron repulsions in that anion are a little bit easier to bear as you get to bigger and bigger atoms. But that is the electron affinity trend. There are a lot more exceptions than there are for the other types of periodic trends, so it's a little bit more difficult to just use the periodic trend to explain the answer, but there they are. Okay, the next thing we'll do is look more at ions. So ions are, I think, a little bit easier to understand than neutral atoms in most cases. There are some tricks, but as long as you recognize that you have ions, they should be relatively easy to deal with. So here's some observations. Atoms are larger than their cations. So Li to Li plus. When we make a cation, the atom gets smaller. In this case, a lot smaller, going Li to Li plus and Na to Na plus. And for cations here, we go from iron to iron 2 plus to iron 3 plus. The bigger the charge, the smaller the radius. So try to explain those using what you know about periodic trends and the different forces, Z effective, all that. Okay, so to explain this, well, what are we actually doing when we're making a cation? To go from Li to Li plus, we're removing an electron. Remember that it's the electrons that determine the size of the atom, and in this case, since all we're doing is adding and removing electrons, anytime we're going to remove an electron, that's going to make the electron cloud smaller, right? You think about like, pouring liquid into a glass or something like that, or tearing layers off of an onion. The electrons are what's setting the size of the atom, so when you pull the electrons away, you have less electrons and you have a smaller cloud of electrons. Again, just think about pulling some of your cloud away. So that's pretty clear. Because the electron cloud sets the size of the atom, whenever you remove any of those electrons, the atom has to get smaller. That explains both of these different observations. Now we can go a little bit more detailed to explain this. If we look on the left, going from the neutral atom to Li plus and Na plus, these are big decreases in size. Why is it such a big decrease in size? Well, lithium is 1s2, 2s1. Li plus is just 1s2. So in this case, we removed that whole n equals 2 shell. that n equals 2 shell was much further from the nucleus, much more spread out, and now we're just to this very, very small 1s orbital is the only thing that's left. So because we removed that whole valence shell, we saw a big decrease in size. Same thing for Na+. Using that visualization here from js.munano.org, we can again see this is the sodium. That 3s1 electron is very far from the nucleus, held very weakly. When we remove it, we're left with just this core. This is the sodium plus, much, much smaller than the neutral sodium atom. Now for iron to iron 2 plus, same thing. We're removing those 4s2 electrons. When we go from iron 2 plus to iron 3 plus, we're removing one of the 3d electrons. So this is from argon 3d6 to argon 3d5. Again, anytime we remove an electron, that electron cloud is going to get a little bit smaller because there's just less electrons in the electron cloud, but it's a smaller effect here. Still gets smaller, there's less repulsions among that cloud, and just less electrons in it, but not as big of an effect as removing a whole shell of electrons. Okay, atoms are smaller than their anions. Explain that observation. So to explain this, again, we're going to form an anion by adding an electron, or 2 electrons in this case, for oxygen to O2 minus and S to S2 minus. That's what we're doing. We're adding electrons. Well, anytime we add electrons, that's going to make the atom bigger. In this case, it actually makes it much, much bigger usually, and that's because electrons repel each other. So adding those extra electrons is going to increase those electron repulsions, and electrons have to stay much, much further away from the nucleus to account for all those added electron or electron repulsions. So yeah, those electrons must spread out to minimize electron repulsions. This is a fact that we would sometimes sort of include in terms of our Z effective idea, right? Just in terms of the fact that Z effective is that balance between the protons in the nucleus and the electrons. More electrons is always more repulsions and always a weaker force holding the electrons to the nucleus. So here, for oxygen, we have 8 protons and 8 electrons. For O2 minus, we still have 8 protons, but now we have 10 electrons. Those 10 electrons means we have much more repulsions, and again, we have to make the atom much, much bigger when we form the anion, just to minimize those repulsions as best we can, keep the negative charges as far apart as possible. Okay, now looking at anions versus cations, so the trends work the same as with atoms if we compare cations to cations and anions to anions. So from N3 minus to O2 minus to F minus, the size decreases. Na plus to Mg2 plus, the size decreases. But in general, you can see here that anions are usually bigger than cations. That's because anions have those extra electrons and have to spread out to minimize those repulsions, whereas cations usually have lost a complete valence shell, and so whereas neutral atoms over here are quite large because they have 1 or 2 weakly held valence electrons, when we remove those valence electrons, we have a small core electrons left over that end up being quite small, held in quite close to the nucleus here. So that's the general trend. Isoelectronic series are a nice case. These are relevant because these are a lot of the common ions we actually work with in the lab, things like Na+, Mg2+, F-. What trend do we observe, and explain the observations? Okay, the trend is pretty straightforward here. From O2 minus is the largest, Mg2 plus is the smallest. Now why? Well, they're isoelectronics. They all have the same number of electrons, but we have more protons here as we go from O2 minus to Mg2 plus. So if we want to explain the observations, well, more protons, same electrons, equals larger Z effective, right? More protons in the nucleus are going to pull those electrons in tighter. So for O2 minus, we have 8 protons in the nucleus, a plus 8 charge on the nucleus. Whereas for Mg2 plus, that one we have a 12 plus charge in the nucleus. In the same case here, we always have 10 electrons, so 10 electrons here have to spread very far out. There's only 8 protons they're attracted to. Here we have 12 protons, and those electrons are going to get pulled in very, very tight because of the strong force between the electrons and the 12 protons in the nucleus versus only 8 for O2-. So more protons for the same electrons is a larger Z effective. So yeah, that means that larger force pulling the valence electrons is going to mean that the valence electrons are held closer to the nucleus. Again, that sort of ratio of electrons to protons is another way to think about it. 10 electrons versus 8 protons, we've got this negative charges that we've got to stay very, very far away. When we have 12 protons here, that's going to let those same 10 electrons get held in very, very tight. That's worse for repulsions, but it's worth it because it lets them stay close to that big positive charge in the nucleus. Here's that same information in this sort of visual form. Oxygen has these 10 electrons held pretty weakly because of only 8 protons. As we keep cranking up the protons, that keeps squishing down the size of the overall ion. Okay, let's end with another exercise. Take a few minutes to try these on your own, and then I'll show the solution. Okay, when you're doing these, I would always say the first thing you want to think about is, are these neutral atoms or ions? If they're neutral atoms, we can use our normal rules. Remember that force increases going up and to the right. We're thinking about radius right now. Radius is actually going to increase the other way, since bigger force is going to be equal to a smaller radius. So again, this is going to apply for neutral atoms only. But we do have neutral atoms here. So selenium versus calcium. Selenium is over here at 34. Calcium is over here at 20. So again, calcium is going to be bigger. Now the Y, right, for neutral atoms, remember the key thing going on as we go up and down the periodic table is that here we're going to be in smaller N as we go up the periodic table. As we go to the right, larger Z effective, right? Again, for neutral atoms, that's always a good explanation. Larger Z effective then is going to explain the difference between selenium versus calcium. So selenium has a larger Z effective, which is a stronger force holding the valence electrons, which is going to mean that selenium is going to have a smaller size because that stronger force is going to hold those electrons in closer to the nucleus. So that's why calcium is bigger, because of its smaller Z effective. Again, we're in the same shell N, so even though shell has a big impact on radius, it's the same shell N, so that doesn't have any impact here. Now for 2Cl versus Cl minus, so we don't have any difference in atom here, but for Cl versus Cl minus, we think about the difference between those. Cl minus has 1 extra electron. Remember, the size of the atom is governed by how big the electron cloud is, so it has 1 extra electron equals a larger electron cloud, right? More electrons is going to mean it's a larger electron cloud is equal to a larger radius. So pretty simple there, as long as you remember what radius is and what's going on when you're forming anions and cations. Again, you could also bring in electron-electron repulsions. That's also a very important factor. That extra electron is going to cause more repulsions, which is going to cause the electrons to spread out even more and the radius to get even bigger. But more electrons equals a larger cloud also works. For the next one, Br minus versus Sr2 plus, those are ions, so we can't just say, hey, Br is higher in the periodic table than Sr, so Br is going to have a smaller radius. Because these are Br minus and Sr2 plus, we need to look at the electron configuration of each of those ions. When we look at the electron configurations of the ions, Sr2 plus goes back to losing 2 electrons, goes back to krypton, and Br minus is also going to gain an electron and also achieve krypton. So these are going to be isoelectronic. They have the same electrons, but Sr2 plus Sr is atomic number 38. So compared to Br minus, it has 3 extra protons, 38 versus 35. And therefore, when we think about Z effective, or that ratio of protons to electrons, we have extra protons in the nucleus. That's going to increase the effective, give us a bigger pull on those same 36 electrons, and that's bigger pull from the larger Z effective is going to pull those 36 electrons in closer and make SR2 plus a smaller size, and therefore Br minus is the larger of the two. So when you think about isoelectronic ions, the only difference is the number of protons. More protons is a bigger pull, larger Z effective, larger force, and therefore a smaller size. Okay, list the following in order of increasing radius. So most of these are neutral atoms, so we can use our rule here, where this is bigger force, and going this direction is larger radius. So we can use that to get a good start on this if I just highlight our atoms. So highlighting those and placing them from smaller to larger, we have fluorine, bromine, chromium, and cesium. Next, we need to think about SR2 plus, our ion. So SR2 plus is going to then achieve a krypton configuration. Now, SR would be quite large. It would definitely be larger than bromine. It would be, I guess, just sort of slotting in here between between Cr and cesium. But SR is actually going to be, SR2 plus is actually going to be quite small. It's got one extra electron compared to Br, but a couple extra protons. So probably smaller than Br, and SR2 plus is probably going to slot in somewhere in here. Maybe one way to think about that is that if we just had krypton on this table, bromine, krypton is to the right, krypton is smaller than bromine, and SR2 plus is actually going to be even smaller than krypton, because it's the same electrons as krypton, but 2 extra protons, which is going to pull those electrons in even smaller. So SR2 plus would be even smaller here, much smaller than bromine, and again, not as small as fluorine, but definitely the second smallest out of all these options. Okay, one of the things we get out of these periodic trends is also trends in reactivity. So group 1 has these same typical M2O type compounds. In lab, you're going to work a lot with different types of compounds. Group 1 and group 2 compounds, very, very commonly, you exist as those +1 or +2 ions. Similarly, halogens in group 7 exist as -1 ions in solution that we work with quite a bit. And group 8, the noble gases, have limited reactivity and are very stable. As we go forward, we'll see again the consequences of the way the atoms are structured according to quantum mechanics in terms. Okay, so here's one of our summary slides in terms of some of the key trends going on here. You can definitely draw these arrows on your periodic table. Remember, though, that these trends apply for neutral atoms only. So you can certainly draw these trends for force, for ionization energy, for radius, for things like that. But again, remember to take into account that those only apply for neutral atoms.